All right. Good morning. Welcome to my talk. I'm here to present CloudMatcher, a cloud crowd service for entity matching. My name is Yash, and this is a joint work with many folks from Marshfield Clinic and Johnson Control. To get us started, just a second. All right. To get us started, let me briefly review what entity matching is. Entity matching identifies data instances that refer to the same real-world entity. As an example, given two tables containing drug description, our goal is to identify if this record in table A matches with this record in table B, and this record matches with this one. Entity matching is an important problem in many domains, and it's particularly critical in health informatics application for matching genes, proteins, and patients in EHR and so on. So it's a well-known problem as it raises both accuracy and scalability challenges, and so it has been studied intensively over the years in many communities such as AI, database, and KDD. And as a result, many such EM algorithms have been proposed. And building on top of these algorithms, many systems have been developed. However, it is still very difficult for domain scientists or the users to use such systems. First, because the setup of these systems is generally non-trivial and time-consuming. They do not scale to large tables, and the systems that scale to large tables are often supported by a cluster of machines, which the user or domain scientist they don't want to manage. Often these systems require some EM expertise. They want the user to know what a string matching is, when to use which machine learning model, what features to use, and so on. And finally, they do not allow collaboration with crowd or a team of people. So to address all these problems, our solution was to build CloudMatcher, a cloud crowd service for entity matching. CloudMatcher allows user to match two tables by letting the users do very less work. And we envision CloudMatcher to be simple, easy to use, scalable, and highly available service on the web. So let me show you a quick demo. So the user logs into CloudMatcher. To perform an EM service, he needs to have two tables in CSV format right now. And let's say the user is matching two restaurants data sets A and B. Here, each row represents a restaurant. So the user begins by uploading table A, followed by table B. And since we use a learning model, we ask user to supply at least two positive and two negative examples. We use these seed examples for active learning. So for those who know, active learning runs in iteration, and in each iteration, the system identifies a set of controversial tuple pairs and asks user to label it as match, non-match. And if he's not sure, he can also say I'm unsure about it. So once the active learning iteration is done, we apply the model on A and B, both the tables, to get the predicted matches. As we can see, the table ID 534 matches with table ID 219 and so on. So as we saw in the demo, it's very easy to use. The user does not have to learn or set up any complicated systems or cluster. It's very straightforward. No EM knowledge is required to use CloudMatcher, as the user performs simple actions such as labeling a tuple pair as match, non-match, uploading a data set. Alternatively, he or she can also pay to outsource the work to a crowd of workers. This is known as crowdsourcing. And in CloudMatcher, we use Amazon Mechanical Turk for. Finally, it scales. It can handle tables of millions of tuple and can automatically add machine resources as and when required. So the current status is that we have deployed version 1.0 at cloudmatcher.io, and it's being used at different departments at UW and affiliated research institutions. And we also plan to open source the code in near future. So CloudMatcher is very easy to use from outside, but underneath it has a lot more complexity. And to explain this, let me start by introducing the basics, important steps of entity matching. So in practice, most of the EM steps have like two steps, blocking and matching. So let's say we have two tables A and B. Table A has three tuples and table B has two tuples. So in practice, A cross B is often very large, and considering all the tuple pairs in it is highly impractical. So the idea of blocking is to remove obviously non-matched tuple pairs from it. So here we can see in the example, two tuple pairs have been removed from 6 possible combination. And going back to the restaurant example, one of the blocking heuristics could be that if two restaurants disagree on a state, they do not match. For each of the surviving tuple pair, the matching step then predict whether it's a match or not match. So in practice, today, to do blocking, most of the current systems would require a developer to examine table A and B and then come up with blocking heuristics. And then the developer would programmatically code and execute them over A and B to get the candidate tuple pairs. So as you can notice, it makes it very difficult for an organization to concurrently deploy multiple crowdsourced CM solution, because it needs developer for every crowdsourcing task, and we don't have enough developers around. So our recent solution, Corleon, crowdsources the entire EM workflow, thus requiring no developers at all. So here the blocker module uses crowdsourcing to learn such blocking rules. So it basically asks crowd to label a set of tuple pairs, and based on that it learns a classifier, and from which it extracts rules. And finally it applies it to A and B to get candidate tuple pairs. The matcher also does active learning and apply the classifier on candidate tuple pairs to get predicted matches. So this is a completely hands-off crowdsourcing solution. So let's zoom into the blocking module a little bit, because that's what we use in CloudMatcher. So it starts by taking a small sample S from A cross B, because learning over A cross B is impractical. It's going to be huge. So it trains a random forest F on S using active learning and then extract candidate blocking rules from it. So as we can see here from the two decision trees, if the two book data sets do not agree on ISBN, then they don't match. And if they agree on ISBN but not on the number of pages, then they are not matched. And similarly, the other two rules we extract from the other decision tree. So next, the system basically used the crowd to evaluate the precision of extracted rules, and finally select a subset of it to execute over A and B. Now A cross B can be large, and to execute the rules in a scalable manner, we need to use some big data framework. And we talk about this in our paper in Sigmod 17 Falcon. So based on the foundations of Corleon and Falcon, we developed a workflow for CloudMatcher which looks like this. It uses the concept of blocking that I just explained. And this looks complex, but we do it to maximize the opportunities for crash recovery, fault tolerance, and optimization. But one thing to notice here is that this workflow has a lot of user interaction tasks in between. So these user interaction tasks, they do not take a lot of machine time to execute. But what if the user decides to stop in the middle, go out for lunch or on a phone call? These steps can take a lot of time. They can hog resources until the user responds. And the same goes for any crowdsourcing task as well. So we had the workflow for CloudMatcher. Then we decided to look into the popular workflow management systems out there like Airflow, Luigi, and stuff. And we found out that these existing systems cannot handle a workflow with user interaction tasks in between efficiently, because they were designed to just run batch-related tasks. To solve this problem, we developed an architecture for CloudMatcher which looks like this. So here the meta manager is a key component which is responsible for executing the end-to-end workflow. What it does is that if you submit a task, it will convert it into a workflow and will partition it into pieces such that each piece is either a user interaction task or a batch task or a crowd-related task. And then we'll use the appropriate engine to execute that task. And together, both Meta Manager and these engines coordinate the management of failure and crash recovery using the metadata store and data store. So let me talk about evaluation a little bit here. So we evaluated CloudMatcher on 4 real-world data sets which came from a non-profit organization, then from Johnson Control and Marshfield Clinic. And we have deployed CloudMatcher in a very typical Amazon EC2 node cluster with typical Amazon Mechanical Turk settings. So here's the overall performance. The first point I would like to make is, if you see the cost, it's very reasonable, and so is the total time. But the performance actually varies. For the people dataset, CloudMatcher is able to get good numbers on precision recall with low cost and low time. But for address, the recall is low, and it turns out that the data is dirty. This suggests that we need some cleaning before feeding into CloudMatcher. For vendors, the precision is very, very low. And we found out that the vendor dataset had some portion of data from Brazil, which was super dirty, and that was killing the precision. So we removed the data from Brazil and actually ran CloudMatcher again, and we were able to get good numbers for precision and recall. And this kind of emphasized that data cleaning is, it's a must. Then the last one is really interesting. It came from Marshfield Clinic because the data here is sensitive. The user was, so we had to label it in-house, and the user was able to label more than 1,000 tuple pairs in 1 hour 10 minutes, which is very little and doable. The other thing to notice here is that after blocking, the candidate set was huge, and this attributes to a huge machine time. So this kind of suggests that there's a lot of room for machine optimization, and right now we are working on that. So with that, let me conclude my talk. In this talk, I have kind of argued that EM is very critical for health informatics application, and current systems, and have shown that current systems have some limitations and are difficult for domain scientists or a normal user to use. So we have developed CloudMatcher, which is a cloud crowd solution, and we believe that this is one of the first solution out there which is providing both cloud and crowd service. The initial results look promising, but there's a lot of things to work on, and the paper also mentions a lot of interesting lessons learned that I would recommend you to please look into. And we are working on it, and we plan to open source the code soon in near future. And that concludes my talk. Thank you.